Manipulating and graphing rational expressions. Be aware that in many of these methods, the first step is to factor. Adding and subtracting rational expressions. Step 1, manipulate the fractions to have the lowest common denominator, which in this example, I did here, these couple steps. Step 2 would be to add or subtract the numerators, which I did, and then simplified. Subtraction is the exact same. I added them up here, found the common denominator here, added them up, got the answer here. Common mistakes. Probably the most common conceptual error made while doing this problem is forgetting to properly flesh out the denominators or numerators, leading to an answer that is incorrect, or forgetting multiplying and dividing rational functions. This is pretty much the exact same as multiplying and dividing normal fractions, except the factors are more complex. As shown, you can same rules apply pretty much all the way through. Some common mistakes. You could simplify incorrectly. That's very common. For example, when non-like terms are removed under the guise that you think that they are like, forgetting to flip the second fraction when dividing, or forgetting a term. Evaluating rational expressions. Step 1, find the common denominator and multiply it through the function. Step 2, algebraically solve for x. Step 3, check the solution if it is extraneous, and you do that by plugging the solution that you have back into the equation, and if it causes the equation to not exist at that point, then it is extraneous. As you can see, I've done that here. Multiply common denominator, then algebra, not extraneous. Common errors is not checking if the solution is extraneous. Long division, a technique used to divide functions by other functions, in particular polynomials. Step 1, set up the functions like so. Make sure that the terms are written in descending order of their degrees. Step 2, divide the term in f of x with the highest degree by that of g of x. Step 3, multiply the answer by g of x. Step 4, subtract the thing obtained in step 3 from f of x. Repeat steps 2 through 4 until you run out of terms with degrees higher than that of the highest of g of x. Step 6, take the answer you have and add the remainder over g of x to it for the final answer. The most common mistake when using this method occurs on step 4. When you subtract, it is very easy to distribute a negative. Yeah. Here are the definitions of each of the function features: domain, range, roots, y-intercept, vertical asymptote, when the denominator is equal to 0, horizontal asymptote, when the highest degree of the numerator is larger than that of the denominator, or when they are equal. The whole, which is when the numerator and the denominator are equal to 0 and you cancel out the factors on the top and the bottom, and the slant asymptote, which you determine with polynomial division, but you disregard the remainder because those always actually go to 0 as x approaches infinity, since they get infinitely smaller. Next, end behavior, which is denoted like that in IM3, but in calculus it's denoted with limits, particularly limit as x approaches plus or minus infinity of f of x. Even functions, a function where f of x is equal to f of negative x on the domain of f of x, and an odd function, a function where f of x is equal to negative f of negative x on the domain of f of x. Here are a couple of examples where you put all the previously mentioned methods and ideas to practice. In this example, you got a vertical asymptote, a horizontal asymptote. You figure that out by evaluating this function down to here, and you also have to get the domain, the range, the root, the y-intercept, the asymptotes as previously mentioned. There's also a hole here. You have to cancel that out, which you can see here, as well as the end behavior, which, as you can see, as x goes to negative infinity, it goes to -2, as well as when it goes to infinity. And you can see in this example that we have a slant asymptote, which you have to use polynomial division to get, and it's a little messy, but you disregard the remainder, of course, and you end up with the slant asymptote of -x/4 minus 1/4, and it goes like that. And remember, it's only on its effective domain that the line cannot touch it. And lastly, over here we have a couple of even or odd questions. Pretty simple stuff. Function features. Common errors. One common error would be to confuse open and closed intervals. This is a pretty simple error, but it's still pretty bad when you do it. When factoring, misplacing, or forgetting a negative leading to an incorrect perception of the roots or vertical asymptotes. You could also forget to cancel like terms on the numerator and denominator when they imply a whole. This leads to a root and a vertical asymptote on the same x value, which is impossible. Next, you could perceive the horizontal asymptote to be effective where it is not. This pretty much makes the function impossible to graph. And lastly, when evaluating the slope of a slant asymptote, messing up the long division as mentioned previously.